Question 13, Part C. A golfer hits a golf ball with initial speed v meters per second at an angle theta to the horizontal. The golf ball is hit from one side of a lake and must have a horizontal range of 100 meters or more to avoid landing in the lake. Neglecting the effects of air resistance, the equations describing the motion of the ball are x equals vt cos theta and y equals vt sin theta minus half gt squared, where t is the time in seconds after the ball is hit and g is the acceleration due to gravity in meters per second per second. Do not prove these equations. Part 1. Show that the horizontal range of the golf ball is v squared sine 2 theta over g meters. The first thing we need to do is to find the flight time of the golf ball. Now, since the golf ball is projected from level ground and lands on the same level ground, we can solve y equals 0 to find the flight time. So when the golf ball is projected, at the point of projection, the golf ball is actually on the ground, so it's 0 meters above the ground. And when the golf ball lands, it's also 0 meters above the ground. And we're only interested in values of t greater than 0, so t itself is not equal to 0. So given the equation y equals vt sine theta minus half gt squared, so this is the displacement equation in the vertical direction, we can solve 0 equals vt sine theta minus half gt squared for t. Rearranging this equation to isolate vt sine theta, we get vt sine theta equals half gt squared. Dividing both sides of the equation by t, because we're interested in positive values of t, we get v sine theta is equal to half gt. And then rearranging this equation to make t the subject, we get t is equal to 2v sine theta over g. So that's 2v sine theta over g seconds that the golf ball is in the air. So using the horizontal displacement equation, x equals vt cos theta, we can proceed to find the range. Now, using the value of time that we found here, we substitute this for t in the displacement equation here. So x is equal to v times 2v sine theta over g times cos theta. Now, rearranging this equation slightly so that I can group together 2 sine theta cos theta, and we get v squared because we have this v here multiplying this v there, and that's over g. So x is equal to v squared over g times 2 sine theta cos theta. And recall that sine 2 theta is equal to 2 sine theta cos theta. This is the double angle identity for sine. So we can replace 2 sine theta cos theta with sine 2 theta. So the range x is equal to v squared sine 2 theta over g. Therefore, the range is v squared sine 2 theta over g meters. An alternative solution to part 1 involves using the property that the vertical velocity of the golf ball is 0 when the golf ball reaches its maximum height. Now, the time that it takes for the golf ball to go from level ground, or the point of projection, to its maximum height is equal to the time that the golf ball takes to go from its maximum height back down to level ground when it lands. So if we can find the time that it takes for the golf ball to go from the point of projection to its maximum height, all we have to do is to double it and we get the total flight time. So at the maximum height, y dot, which is the vertical velocity of the golf ball, is equal to 0. So the time to its maximum height may be found by solving the equation y dot equals 0. Now, the vertical displacement equation is y equals vt sine theta minus half gt squared. Differentiating y with respect to t, we get y dot is equal to v sine theta minus gt. So solving 0 equals v sine theta minus gt, so we're solving for t. We rearrange this equation to make t the subject, we get t is equal to v sine theta over g seconds. That's the time it takes for the golf ball to go from the point of projection to its maximum height. We'll call this equation number 1. Now, the total flight time is found by doubling this value here. So twice equation number 1. So 2t is equal to 2v sine theta over g. The remainder of the solution to part 1 is identical to the previous solution that I presented. So the range is found by substituting 2v sine theta over g for t in the equation x equals vt cos theta. And the rest of the solution is identical to what I presented in the previous solution to part 1. And we get the range is equal to v squared sine 2 theta over g meters. Part 2. Show that if v squared is less than 100g, then the horizontal range of the ball is less than 100 meters. From part 1, the horizontal range of the golf ball is v squared sine 2 theta over g, which can be written as v squared over g times sine 2 theta. I'll call this expression number 3. Now given v squared is less than 100g, dividing both sides of the inequality by g, and g being a positive value, we get v squared over g is less than 100. So the v squared over g here can be replaced with 100. So from expression number 3, we get the range is less than 100 times sine 2 theta. Now it's important to note that sine 2 theta is less than or equal to 1. So the maximum value of sine 2 theta is 1. So if we consider the maximum value of sine 2 theta, that means 100 sine 2 theta must be less than or equal to 100. Therefore, the range is less than 100 meters when v squared is equal to 100g. It is now given that v squared equals 200g and that the horizontal range of the ball is 100 meters or more. Part 3. Show that theta is greater than or equal to pi over 12 and less than or equal to 5 pi over 12. It's given that the range is greater than or equal to 100 meters and v squared equals 200g. Now, rearranging this equation to isolate v squared over g, we get v squared over g equals 200. Now recall from part 1 that the range of the golf ball is v squared over g times sine 2 theta. Hence, v squared over g times sine 2 theta is greater than or equal to 100 based on this condition here. But we know that v squared over g is equal to 200. So replacing v squared over g here with 200, we form the inequality 200 times sine 2 theta is greater than or equal to 100. Dividing both sides of the inequality by 200 to isolate sine 2 theta, we get sine 2 theta is greater than or equal to half. Now this implies that 2 theta is greater than or equal to pi over 6 and less than or equal to 5 pi over 6. Dividing all terms in this three-way inequality by 2 to isolate theta, we get theta is greater than or equal to pi over 12 and less than or equal to 5 pi over 12 as required. Now this can be observed in the graph of y equals sine 2 theta. The period of y equals sine 2 theta is pi radians. So a half cycle occurs from theta equals 0 to theta equals pi over 2. A full cycle is from theta to pi radians. And we're interested in the values of theta where sine 2 theta is greater than or equal to 1 over 2. And that's this shaded region here. And that occurs from values of theta greater than or equal to pi over 12 and less than or equal to 5 pi over 12. Part 4. Find the greatest height the ball can achieve. We need to find the time it takes for the golf ball to reach its maximum height, and that occurs when its vertical velocity y dot is equal to 0. Now the time to maximum height is found by solving the equation y dot equals 0 given the vertical displacement equation y equals vt sine theta minus half gt squared. So to get the vertical velocity equation, we differentiate y with respect to t. So differentiating y with respect to t, we get y dot is equal to v sine theta minus gt. Now we replace the y dot with 0 because that's the vertical velocity of the golf ball when it reaches its maximum height. So we form the equation 0 is equal to v sine theta minus gt. Solving this equation for t, and we do that by making t the subject, we get t is equal to v sine theta over g. And we'll call this equation number 1. Now, alternatively, the time for the golf ball to reach its maximum height may be found by halving the total flight time that we found in part 1, which was 2v sine theta over g. Dividing that by 2, we also get v sine theta over g. So we can do that without differentiation. So from equation number 1, that's this equation here, I'm going to replace the t variable in the vertical displacement equation here and here with this value of t that we found here. So from equation number 1, y max, which represents the greatest height of the golf ball, is v times v sine theta over g times sine theta minus half times g times v sine theta over g in brackets squared. Expanding the brackets, we get y max is equal to v squared over g times sine squared theta minus half times g times v squared sine squared theta over g squared. Now, g over g squared is 1 over g. So the equation simplifies to y max is equal to v squared over g times sine squared theta minus v squared over 2g times sine squared theta. Notice that this term is half the value of this term. So we get y max is equal to v squared over g times 1 over 2 times sine squared theta, where v squared over g is equal to 200. So replacing the v squared over g here with 200, we get y max is equal to 100 times sine squared theta. Now, sine squared theta is an increasing function for values of theta greater than or equal to 0 and less than or equal to pi over 2. But theta can only take on values greater than or equal to pi over 12 and less than or equal to 5 pi over 12, which is inside this interval here. Hence, y max, which is the greatest height of the golf ball, occurs when theta is equal to 5 pi over 12. Therefore, the greatest height is 100 times sine squared 5 pi over 12 meters.